Hello, I want to have a video to try to draw some examples for you of Lenz's law, just because it's a very visual sort of thing to get across to students. And just doing it through like some slides in a PowerPoint or something, it really doesn't work very well. So what I'm hoping to do here is just give you an idea of how to apply this thing called Lenz's law to situations involving solenoids. And the easiest way to kind of think of Lenz's law is essentially the universe is never going to let you get something for nothing. In Lenz's law, when we look at the two possible answers that can come out of any situation that we're given, you have to pick the one that basically makes it difficult, that makes things hard to do. Because if you're looking at a situation where it's like, oh, that was easy, it means that the universe is pulling magnets in for me, or it's making electricity for free for me, then it's the wrong way. It always has to be that we're fighting against things to be able to get the current to flow or to push the magnet in. You'll see what I mean when I start drawing the diagrams of this. Now, we are going to be drawing sort of the traditional solenoid diagrams. So a tube, and it's got a wire going around like this. Okay, now the most important thing that I want you to understand in this first example I'm going to do is that right now there's no current going through that wire. This isn't like we're saying put current into the wire and let's see what this does as a solenoid. Instead, what we're trying to do is use magnets with this solenoid to make electricity flow in the wire. So I'm going to grab a magnet, just a bar magnet, and I'm going to show it this way with the north on this end, south on this end. And the idea being that the solenoid itself is really a solenoid. It's a tube. Okay, this is empty inside. So what I could do is actually push this magnet into this opening. It would actually go into the tube if I wanted it to. We always start these questions though with the idea of, right now it's not inside the tube, but in this example, I'm going to push the magnet in towards the tube. So we start imagining what this could mean. And remember that whenever you're doing anything with solenoids or whatever, if you have some sort of tube-shaped object or a water bottle or what, something that you can hold, it's probably going to kind of help you out with this a little bit more. So one possible solution to this is that the current will be going up in front. Okay, so up in front in the wire, which you can see where my thumb's kind of sticking out over here. That would make this end the north end. Now let's just kind of sketch that out as a possible answer. I'm not saying that that is what's happening, but if doing this caused current to go up in the wire, this end would be north, this end would be south. That's the way that the current would induce magnetic poles in the solenoid. So I look back and I say, well, does that make sense according to Lenz's law? In this case, the north and the south end here are near each other. That means that as I pushed the magnet in, it would induce the current to start flowing, making this end south. And then I could let go of the green magnet. It would pull itself in because it's making it easy to do. The north and the south would attract each other. I could let go of the magnet. It would continue to pull itself in while making electricity for me. That's not what's going to happen. Because remember, Lenz's law says to us it's going to be difficult. You're not going to get something for nothing. So let's take that and apply it, see if it works, if we suggest that the current is flowing in the opposite direction. Because if once again I grab the tube and I say that now the current is going down in front, my thumb is pointing that way, making this end the north end. So pushing the magnet in makes the current go. It induces the current flow that causes this end to be north and this end to be south. Now check it out, north and north. It would be difficult to push this magnet in. I'd have to keep on pushing. And in fact, the harder I push, the more current is going to flow. which makes this North Pole stronger, which makes it even more difficult. I would actually have to keep working harder and harder to push this green magnet in. That's the actual answer then. This is what would be happening, because whatever we're doing, it's going to make it difficult to do. So let's look at another possibility here. Okay, I'm going to get rid of those, and I'm going to say, what if instead of shoving the magnet in, same magnet, same solenoid, now I'm pulling the magnet out? Okay, this would be kind of different because we're kind of assuming that the magnet had been inside the solenoid, and we've drawn it out, we're pulling it out. So what would make that difficult? Well, if we do the current the same direction that we just did, that would actually make it easy, because this end would be north, and it would actually push this magnet away from me. I would be getting something for nothing. So let's go back to that first way that I drew it out with the current going up. If I do current going up, this end is north, this end is south. That would make it difficult, because as I'm pulling this green magnet out and it induces the current flow up in front on the solenoid, this end would become south, which would pull back on that north, right? It's going to try to pull back on the green magnet while I'm trying to pull it out. That would make me pulling the green magnet out difficult to do. So yep, this is the solution. This is the direction that the current would be flowing. Now sometimes we don't show it that way, okay? I mean, we don't show like I'm doing this with the magnet and everything's labeled. So instead, let's say, I'm going to kind of erase this and kind of get it back to a starting point. Let's say instead, all that I showed you in the diagram is that I'll say that the current is going up in front, and I tell you that all that I know is I'm pushing the magnet in, but I don't know the poles on the magnet. Now, we already know the answer because we had just figured this stuff out. But this could be the beginning of the question, where we still know the direction the magnet's being pushed, but we don't know which pole is which on the magnet, but they have given us the current flow that's being induced in the solenoid. It's this idea that they always have to give us two of the three things. So if they're doing this, don't start over here with the magnet. We don't know what's going on with the magnet yet, but I can figure out things for the solenoid, because once I know the current is going up in front, I know that my thumb's pointing this way. That means that this is the north end and this is the south end. Once I've identified that, I can go, well, what would make that difficult? What would make it hard to push this magnet in closer to this south pole? It would be difficult to do that if that end was south also. So that's how I can figure out which direction is which on the poles of my green magnet that I'm shoving in. Okay? Or, to take it back a step again, they tell us that this is the arrangement. They would actually tell us which poles are which on the green magnet. They tell us the current, but they don't tell us, are we pushing the magnet in or are we pulling it out? So again, I would have to start with, hey, let's look at my solenoid. Current is going up in front, thumb is pointing that way, meaning that I know this end is north and this end is south. And then we could go, wow, what would be difficult to do? Pull this away? No, because the south and south repelling would make that easy. Trying to push the magnet in, south to south, would be difficult. Oh, I figured out which direction we're pushing the magnet. Okay, so it's always going to be one of the three things that we essentially don't know. The other thing not to get freaked out about is if they show you the solenoid arranged vertically, which is something we can do with solenoids. So we have a solenoid like this, just drawing in some wiring there. Okay, and maybe they tell us, for example, I've got my magnet up here. I'm going to say this end is south, this end is north. And you know what? Just because it would be easy to do, I'm going to say that I just let go of the magnet so that it's dropping into the solenoid. So I don't even have to be pushing it anymore. I'm just letting it fall. But you know what? Even though I'm not the one actively pushing down on it, it's just the force of gravity doing stuff now, right? And as much as it's the force of gravity instead of me, the solenoid doesn't care. All it's looking at is, wow, I'm going to resist whatever's trying to be done. So if this is going in and it's trying to resist that, what pole would this need to be to resist that? It would be a south end, making this the north end. So now that I know which end is which, now I can figure out the direction of the current. So I'd say I've got my tube, and I've got to have my thumb pointing down, because that's towards north. In front, at least, my fingers are pointing off that way. So the current would be flowing that direction. And remember, when we're drawing stuff on the solenoid, don't draw 73 arrows for the direction of the current. Just drawing one is good enough, because then we know the answer and we understand what's going on. So that's it for Lenz's law. It's all about saying, when you're doing the question, what would make it difficult? What would make it hard for that magnet to move? That might mean that you have to think about the arrangements of the poles on the external magnet we're using, or the direction that it's moving, or something about the solenoid itself. But it's always going to be those three parts that we've got. The solenoid, with its current that's being created by the magnet going in. That current wasn't there before. It's being induced by doing this, which sets up a certain set of poles. The poles on the external magnet itself, and the direction it's moving, either being pushed in or pulled out. What I would suggest is you do a few more examples of these and just kind of get the idea for yourself that it's always fighting against it. That's the best way to kind of rationalize what's going on in Lenz's law. So good luck with that.